So this is the second review video, and today we're going to work on reviewing percent composition, empirical and molecular formulas, and just doing some simple stoichiometry. So let's start with percent composition. Remember, percent composition is just the percent by mass of each element in a compound. And you can do this two ways. You can calculate it using some lab data, or you can use the periodic table. So for example, if you were asked to determine the percent by mass of the elements in carbon dioxide, well, first what you need to know is the mass of the individual elements, and then we need to know the total mass of the compound. So the mass of carbon on the periodic table is 12.01, plus we have 2 oxygens for 32, so 32 plus 12.01 gives us 44.01. So that's our total mass of our compound. So now to figure out what percent carbon makes this up, you're just going to take the mass of carbon, which is 12.01, divided by the total mass, which is 44.01, and then you want to take it by 100%. So 12.01 divided by 44.01 times 100% gives us 27.29% carbon. And then to figure out the percent oxygen, since there's just 2 elements, you could subtract this from 100, and there's your answer. Or you can put 32 over 44.01 times 100, and you'll get about the same thing. So 72.71%. So percent composition is percent by mass of each element in the compound. Now, empirical and molecular formulas are a little bit different. An empirical formula is the lowest whole number ratio of atoms in a compound. So now we could figure out the empirical formula for carbon dioxide just given this data. Okay, so if you didn't know that carbon dioxide was the formula, and you were told that a compound was 27.29% carbon and 72.71% oxygen, and you were asked to figure out the formula. Okay, well, what you first do is just write your percents as masses if they're not given. If we assume we have 100 grams, well, then this would be 27.29 grams of carbon and 72.71 grams of oxygen. Then we need to get mass to moles, so we can divide each of these by the molar mass. So we'll do the same with oxygen. So 27.29 divided by 12.01 gives us 2.272 moles of carbon. If we divide oxygen, we get 4.544 moles of oxygen. Once we get to this step, we can't write these as subscripts in our balanced equation because these aren't whole numbers. So you always, when you get to this step, you divide by the smaller number to make one of the ratios 1. You can see the carbon's 1, and the oxygen's going to be very, very close to 2. Once you get whole numbers, those are our subscripts in our equation. Remember, ones are understood, so your final formula is CO2. So you can calculate an empirical formula. I'm using the percent composition, or if you're just given masses to start, you do the same process. Get them to moles and then divide by the least number of moles. If these aren't whole numbers once you finish, then you need to multiply by a factor to make them whole numbers. Also remember, a molecular formula is just a whole number multiple of an empirical formula, but I don't think you have to do any calculations like that on the final exam. Okay, finally, we can do an example of mass to mass stoichiometry. So if we had hydrogen and oxygen forming water. Good morning. and we were given 3 grams of hydrogen, and we wanted to know what mass of water would be produced using this balanced equation. So first you have to get your mass to moles. This is a 3-step stoichiometry. So the molar mass of hydrogen is 2.02. Remember, we divide there to get that unit to cancel. Now we use our mole ratio in our balanced equation, which in this case is 2 to 2. So you could reduce this down if you would like. Finally, to get to a mass of water, we need its molar mass, which is 18.02. So now we can multiply across and then divide, and we would produce 26.8 grams of water if we use 3 sig figs like what we started with. So this is just an example of a 3-step mass-to-mass problem. Really the only part of stoichiometry that's left is determining a limiting reagent. Okay, so how do you do this? Let's do an example. Alright, I think there's this example in our notes, but we'll just pick different starting amounts. So if we form salt from sodium and chlorine, right, and you are told you start with 5 grams of sodium and you start with 10 grams of chlorine, and you're asked what's your limiting reactant. This means what's going to run out in your reaction, what's going to stop the reaction from forming more sodium chloride. So your first step, we have to get them both to moles. Okay, that's our only method of comparison. So we're going to divide by the molar mass. Now remember, since we have a Cl2, chlorine's diatomic, we need 2 times the mass. So if we plug both of these in the calculator, we get 0.217 moles of sodium, and we get 0.141 moles of chlorine. Now we can't compare these yet because these are 2 different substances. So what we need to do is change one to the other based on your balanced equation. So I'm just going to change chlorine. So in my balanced equation, I have 1 mole of chlorine for every 2 moles of sodium. So if I take 0.141 times 2, this would be 0.282 moles of sodium. So it says, if I converted the chlorine to sodium, this would be 0.282 moles. But how much do I actually have? Well, if I started with 5 grams, I only have 0.217 moles of sodium. So this is my limiting reactant. Sodium is what will run out first, because there's a lot more excess sodium here. 2.82 is larger than 0.217. Okay? So remember, when you do a limiting reagent, you need to get them both to moles and compare those numbers. One will be smaller, that will run out whatever you have extra of. In this case, we would call chlorine our excess reagent. I think that wraps up Unit 6, and we'll look at the solutions unit tomorrow.